of identifying the probability of percolation on the regular tree. So remember, we have a graph which has no cycles and on which every vertex has the same degree. I call it TD, and the degree is D plus 1. Okay, so this is T2. Okay, and yesterday what we did was to say, okay, so I determine one vertex to be the root. If I look at the probability that 0 is connected to infinity, this is equal to the limit when n goes to infinity that 0 is connected to, I think I named it Tn, the set of vertices that are at distance n. And then we computed the expectation of the number of connected vertices at distance n. We computed the expectation of the square of the number of vertices at distance n. And using Pele-Zygmunt inequality, we obtained that if P is larger than 1 over D, then this thing is larger than 0, which is sufficient to say that this limit is positive. Okay, so and the computation of the first moment already gave us that if P is smaller than 1 over D, then theta P is equal to 0. Okay, so now what I'm going to do is to use another method to compute directly theta P. Okay, and I'm going to use as an input that theta P is positive when P is larger than 1 over D, but I don't really need to. There would be some other way to infer that if I wanted to. Okay, but I think this method of computing the moment of a random variable and the moment of the square of a random variable, it's quite general and it can be used. It's something which is very flexible and can be used in many situations. Okay, so at first, what I'm going to compute, what I will want to find is basically to show that theta P is a solution of a recursive equation. And for this, I'm going to proceed as follows. So it will be more convenient to compute the probability that 0 is not connected to infinity. Okay? So let me draw the graph as this. So, okay, so the graph, I can just see it as, well, I have the root. Then I have D plus 1 vertices that are adjacent to the root. And then actually, if I look at these vertices, I can see them as a root of another tree. Okay, so somehow there is a recursive structure underlying there. The problem is that this tree is not exactly the same tree as the one I have at the beginning, because the difference is that this tree is something like this. So the root has degree 2. And the rest has degree 3, but the root has degree 2. So for this reason, I will look at another tree TD, which is not periodic this time, and where the root has degree D. Okay. So this I will call TD. Okay, so I will look at this now in TD, okay? So now, okay, let's call it 1 minus theta p if you want. And once I've computed this, basically, I will be able to go back to the other tree. But this will be, okay, so. Okay. So now what should happen for me not to be connected to, okay, so let's do it for 3. Okay, it will look more general. So if I have a path going from 0 to infinity, then it must be, okay, it must be either a path that goes to V1 and then only uses this subtree, or a path that goes through V2 and only goes to this subtree, or a path that goes to V3 and only goes to this subtree. Okay? If I have none of this happening, I am sure that 0 is not connected to infinity. Okay, so in TD, okay, now I might want to look at my notations. Okay, so let me call E1, E2, E3 these vertices, and let me call these things T1D, T2D, and T3D. Okay? So what I claim is that zero not connected to infinity, well, it's the intersection from I equal 1 to D that, okay, let me first write the complement of the event. So okay, so I want none of this to happen. So I want the intersection of the complement of this to happen. And, well, this is an intersection. So what I have to look at here is a union. Okay, so, okay, so now if I look at the probability, okay, I don't know, maybe I put, okay. You understand that I'm talking about TD now. So this is equal to, okay, to the probability of this intersection. So EI is closed, or VI is not connected to infinity in Ti D. Okay, and now you see that, okay, I might come back to this, but these events, they rely on distinct collections of edges. Okay? So I equal 1 just rely on these edges. I equal 2 edges. And because they are distinct and that the omega E on the edges are independent by definition, then these events are independent. Okay, so the probability of the intersection is just the probability, the product of the probabilities. Okay. Now the other thing is that this thing does not really depend on I, okay, because the graph structure for every branch is the same. okay? And the probability structure on each of these graph structure is also the same. Okay? You have always independent variable with the same parameter. So this thing is just P that E1 is opened or VI is not V1 is not related, is not connected to infinity in TD1 to the power D. Okay, so now I just have to compute this probability. Yes? I have to double check to make sure. Yeah, closed. This is right, this is right, this is wrong. Yes. Okay. So let's compute this probability. So I have a union, so it's not very practical because I have independent events. So what I'm going to do is I'm going to rewrite this as a disjoint union. Okay? So P E1 is closed union the V1 T1D infinity. This is, well, the same thing as yes. Okay? I'm just intersecting here with the complement of this. And now I have a disjoint union. So this is just the probability that E1 is closed. Okay. Probability that E1 is equal to 0 plus the probability that WE1 is equal to 1. Now these two events are independent. Okay, one only depends on these edges in this subtree, and the other depends on this edge. So this probability is equal to 1 minus P. And if I call this probability alpha, this is just P times alpha. Okay. This is P times P V1 T V1 of infinity. But now this tree, it's exactly a copy of the original tree. V1 is its root, so this thing is exactly the same thing. Sorry, here I'm not connected. That's it. Sorry. Okay, and then this by definition is alpha. Is everything clear? Okay, so I promised you an explicit expression for theta p. It's okay, it's only semi-explicit, but It's much better than what you get usually, which is no expression at all. So what we get for alpha is that alpha is a solution of this equation. 1 minus p plus alpha p to the power d. Okay, and now if I look back at my original problem, which was to compute theta p, so the probability that 0 is connected to infinity in theta d, well, it's just equal to, okay, so it's 1 minus the probability that I'm not connected to infinity, and the probability that I'm not connected to infinity is just the probability that I'm not connected by any branches. Okay, so it's for the same reason as before. It's 1 minus p plus alpha p. So 1 minus p plus alpha p to the power d plus 1. So it's equal to 1 minus alpha to the power d plus 1 over d. Okay, where I'm using this equation to replace this by alpha to the 1 over d. Okay, so basically, if I have an expression for alpha, then I have an expression for theta. Okay, here it's just exactly the same computation, except that I have d plus 1 branches instead of d. Okay, so now I have to make sure that I can solve this equation and make sure that I can make sure what theta p is. So I have to know basically what this function here looks like. Okay, I know that alpha is the fixed point of some function, but okay, maybe I would like to know how many fixed points this function has. Any questions so far? So if I look at this function, well, the first thing is that it's convex. Maybe I should give it a name. I don't know. G. So it's convex. I have G of 1, which is equal to 1. I have G of 0, which is equal to 1 minus P to the D. So basically, I have basically two possibilities for this function. So either it looks like this, or it looks like this. So I can have there are only two possibilities. Either I have two fixed points or I have one fixed point. And well, the thing is that I know that 1 is always one fixed point. But I know that when P is larger than 1 over D, alpha is not equal to 1. I know that theta is not equal to 0. Okay, so basically, this tells me that when P is larger than 1 over D, I am in this situation, but maybe I should have another argument to tell you that this is the case. So what you can do instead is compute what the value of G prime of 1. Okay, so if G prime of 1 is larger than 1, then I have to be in this situation. And if G prime of 1 is smaller than 1, I have to be in this situation. Okay, and now G prime of 1, it's what? It's equal to GP. Okay, so this tells me that I have one fixed point if, okay, which is 1. If P is smaller or equal to 1 over D, and 2 fixed point, 0, 1, if P is larger. Okay, so in particular, what I can deduce from this is that, well, okay, first thing, so consequences. The first is that theta 1 over D is equal to 0. Okay, if I have only one solution to this equation, which is 1, this means that theta is necessarily equal to 0. Okay, and this is not something we had with, directly with the first moment method. We could conclude when P was strictly smaller than 1 over D, when P was strictly larger than 1 over D. But if you remember when P was equal to 1 over D, basically the expected number of connected vertices at height n was exactly 1. And it made it difficult to okay, not maybe 1 plus 1 over D, but this doesn't make a big difference. Okay. The second thing is that theta P is C infinity on 0, 1 minus 1 over D. Okay, why is it so? Well, on 0, 1 over D, it's trivial. Okay, so my function is identically 0. And on 1 over D1, basically, I have that alpha is the root which is in 0, 1 of this equation. Okay, so what I'm basically doing is I'm inverting a function, and you have standard theorem of analysis that tells you that well, the inverse of this function is C infinite if the function is C infinite. Okay, I mean, you have to check also, I mean, you have to check the derivatives don't cancel and stuff like that, but this is not really important here. Okay, so in particular, it's continuous. So what you have is that theta p is something that looks like that. Okay, and yeah, the other thing that you can check using this equation is that, yes, when p gets really close to 1 over d, basically, this second fixed point gets close to 1, and therefore theta p gets close to 0. Okay, so it's C infinity. And what will be an exercise will be to show that it's continuous at 1 over d. Okay, so let me check if there are any more things that I wanted to say about this. But I think this is pretty much it. Okay, so exercise. So using this equation and this expression here, show that theta p is equal to 2d3 over d minus 1 square p minus 1 over d plus little o of p minus 1 over d when p tends to 1 over d plus. Okay, so when basically the exercise is use something like Taylor expansion in this equation to prove that this curve here has a slope, okay, and the slope is given by this. D to the 3 over d minus 1 to the square. Okay, so I think this is basically what we are going to see about percolation on the tree, but I'm going to refer back to the tree a couple of times for exercises just to remember that, okay. The behavior on the tree and the behavior on ZD can be different. So now we are going to move back to the general case and with more focus on ZD. And okay, so far what we have seen is that well, there exists a value of p under which the probability that a point is connected to infinity is equal to 0, and above which the probability that the point is connected to infinity is positive. What we would like to say is that when 0 is connected to infinity with positive probability, then it means that you have lots of connections in your system, okay? So it means that in particular, you have, if 0 is connected to infinity with positive probability, with probability 1, you have many points that are connected to infinity in your system. Okay, so this is what we are going to do today. And this is basically the big part of this will be to show that a certain family of events cannot have probability that are larger than 0 and smaller than 1. So as soon as we know that some vertices are connected to infinity with positive probability, we will have an abstract argument that says that if the probability is positive, then it has to be equal to 1. And then we will be able to conclude. So Okay, so I'm going to analyze the existence of an infinite connected component. Okay. Okay, so let me start with an observation. So if I look at the relation x is connected to y, okay, for a fixed realization of omega, this is an equivalence relation. Okay, this is something. Sorry? No, now we are on a general periodic graph, okay? But okay, here it's even more general. But so okay, so this relation of connectivity is an equivalence relation. So basically, we can split our graph G. And these equivalence classes, they are called percolation clusters. Okay, so from now on, when I say x is connected to y, another way to say it is x and y belong to the same percolation cluster. Okay, and I will use Cx to be a set of y such that x is connected to y, or it is the percolation cluster containing x. Okay, and the question that we are going to ask now is, well, what's the probability of having an infinite percolation cluster? Okay. So I'm going to write a result where there are 2 points, but actually there is only one. There is 1 point that we have already proved. Okay, so that's the main theorem that we are going to prove in the remaining of today's time, and it is the following. So I write it. If theta p is equal to 0, then the probability that there exists x such that x is connected to infinity is equal to 0, and 2. Theta p is positive, then the probability that there exists x such that x, okay, x in V. Okay, I will write ZD, but this is valid for any periodic infinite graph, okay? Okay, so this is the main result we want to prove today, and one is, okay, it's not that we have already proved it, but it's relatively easy, so proof of one. Well, what we have is that the probability that the union over x in ZD, that x is connected to infinity, it's equal to, well, it's smaller than the sum when x is in ZD, and the probability of x is connected to infinity. Okay, now I'm going to maybe come back to this in a second, but because our probability distribution, it's invariant by translation on the graph, this is the same thing as the probability that 0 is connected to infinity. Okay, and because of this, of our assumption that theta p is equal to 0, this is equal to 0. Okay, so if 0 is connected to infinity with probability, well, if the origin is connected to infinity with 0 probability, then no vertex is connected to infinity with probability, with positive probability. Okay, so then with probability 1, all the percolation clusters are finite. Okay, so now this is the more important part. And to prove this, we are going to prove actually, well, a more general result. And that's going to have other applications. So I talked a bit about translations of the lattice so far, so now I will introduce a bit of formalism concerning this. So let's consider V to be a vector of ZD. And we define tau V to be a translation operator that acts on 0, 1 to the ED. Okay, so basically it takes an edge configuration and it transforms it into another edge configuration. And the way it does that is that if you want to know what the configuration tau V is equal to on edge E, well, it's just the state of the edge E minus V, where x, y minus V is equal to x minus V, y minus V. Okay, so basically you just shift your environment by a vector V. Okay, so Okay, so now we say that an event is translation invariant for a given vector v if whenever a configuration, an edge configuration belongs to A, then its translated version also belongs to A. Okay, and now this is the same thing as saying that omega belongs to the pre-image of A for this transformation. Okay, so now the main theorem that we are going to prove today is that if A is translation invariant for V, a non-zero vector. Okay, so of course this definition actually doesn't make a lot of sense for V equal to 0. Okay, because then all events are translation invariant, and this does not tell you anything about these events. So if A is translation invariant, okay, and here implicitly I'm assuming that it's measurable, then P of A belongs to 0, 1. Okay, 0, 1 like the couple 0, 1, not the interval 0, 1. Okay, so before proving this, first let us see rapidly how this implies the second part of the theorem. Then I will do a bit of technical preliminaries to introduce the proof of this, to try to make things as clean as possible. And finally, then we'll prove this. So any questions so far with the definitions? Okay, so maybe a question you may have is, why is there a minus here instead of a plus? And yeah, I think basically the answer is coming now. So if you look at the proof of 2, I think with this definition, what we have is that saying that x is connected to infinity for omega, it's the same as saying that x plus v is connected to infinity for the translated environment. Okay, so basically you put a minus here in order to have a plus here, which is nicer. Okay, so saying that x is connected to infinity is the same as saying that x plus v is connected to infinity for the translated environment. So in particular, this implies that there exists y such that y is connected to infinity is the same thing as saying there exists y such that y is connected to infinity for the translated environment. Okay, and this is exactly saying that this event is translation invariant. Okay? If you take A, this event, omega belongs to A is really equivalent to TV of omega belongs to A. But this is just, okay, this is just writing things algebraically, but intuitively it is quite clear. Like, if you have an infinite connected component in your percolation graph, and if you shift everything by a vector, then you will remain with an infinite component. Okay, and if you have no infinite component and you shift it, then you won't create one. Okay, so you don't change the graph structure of the set of the percolated graph after translation. Okay, so now I'm going to do basically a few recalls about notions of measure theory or so. Okay, so the first thing I want to introduce is a symmetric difference. So the symmetric difference between two events is just the union minus the intersection. Okay, and there are a few things that I want to use, and I think these are good exercises. So first thing you can check is that okay, this is true for a general probability, so I will just write P. So for a general probability, you have that the difference between P and A and P of B is smaller than the probability of the symmetric difference. B, so there is no way you can, it's not like union and intersection. There is no way that you can distribute an operation over a symmetric difference, but you have actually the following. So if you take either the union or the intersection of two events and take the symmetric difference with a third one, then what you can do is, well, you can basically distribute this over the symmetric difference, probably provided that you take inclusions. So, and here you have to take the union. So here this is A, B, union, C, union, B, C. And this is A, C, also union. So let me put it, or and this is important. C. Okay, and one way to see this is simply to see that if you look at this event here, this is A union B union C minus A intersection B intersection C. Okay, so when you have this in mind, it's kind of reasonable to see that these things will be included in that. Okay, so this expression is somehow more symmetric than this one, but okay, this is true. And I had some third thing. Yes?
So the proof of becomes a corollary of the theorem because then I just
Oh, yes.
is that existing one y means that is connected to infinity, it will be the same event of 0 being connected to infinity.
Yeah, so okay. There is a, okay. So let me complete the proof and ask me afterwards if this answers your question. So okay, then what we have there is a second ingredient that you need. So here we have said that this event has probability 0 or 1. Okay, we have to check that it has probability 1. So what we have is that the probability that there exists x such that x is connected to infinity. Well, of course, it's larger than the probability than 0 is connected to infinity. Okay, just because this event is included in that. And this is equal to theta p, which is larger than 0. Okay, so this event, it has either probability 0 or 1, but it has a probability which is strictly larger than 0, so then it has to be equal to 1. So thank you very much. This was a serious omission.
It's not going to be equal by the translation of variables instead of greater.
Oh, no, because this event is not translation invariant. The event which is translation invariant is it is that there exists a vertex in my lattice. The event which is translation invariant is there exists a vertex in the lattice which is connected to infinity. Okay? X is connected to infinity is not translation invariant, because if you take the translation of this event, what you get is x plus v is connected to infinity. And these are two different things. Okay, so for instance, you can have a configuration where all the edges around 0 are closed, okay? But this thing is connected to infinity. One of the neighbors is connected to infinity. So yes, basically when theta p is larger than 0, yes, there will be some vertices connected to infinity and some vertices that are not. Yes?
So could you explain again why on proof of 1 we introduce the probability of having x connected to infinity with 0 connected to infinity?
Okay, so here, yes. Okay, so that's okay. So that's okay. I'm going to come back more on this in a second, but here what I'm using is something that I've basically said. Okay, you see, everything is true, but what I'm using here is something which is different. Okay, so let's try to. Okay, so what I'm using here, without saying it, but now I'm saying it, is that this is true for any v and any a. Okay, so this statement would be, okay, my probability distribution is translation invariant. Okay, and okay, I'm going to show you how to prove this in a second. Okay. Okay, so if you remember, okay, in measure theory, basically you have a similar statement for Lebesgue measure. Okay, you have a translation operator on the line, and if you take translation of a set, then you get the same measure. It's kind of a similar statement here, except that our translations are a bit different, you know. But, okay. But yeah, so intuitively this is kind of clear. But yeah, it's better to have a proof, so I'm going to come back to this in a second. More questions? Okay, so I thought there was a third part in the exercise, but apparently there is not. Ah, yes. Oh, yes. Okay, so okay, what I'm going to use is that basically the pre-image of A union B by my translation operator is the union of the preimages, and the same is valid for the intersection, and therefore the same is also valid for the symmetric difference. Okay, and this is more or less a direct consequence of the definition of TOV, which I just erased, but okay, so this is not exactly a property of the symmetric difference, but this is something we are going to use. Okay. So, okay, so now I'm going to introduce a lemma. Which is exactly what you need to prove this. So, what is it? That if A is a measurable event, and n is larger than 1, then there exists an such that the probability of the symmetric difference of A and an is smaller than 1 over n. Okay, so there exists an in A, okay, where A is the set of events that depend on the state of finitely many edges. Okay, so what this means is that B belongs to A. This is equivalent to there exists K larger than 1. There exists E1, EK, such that B, okay, and there exists B bar in 0, 1 to the K, such that B is equal to the event E1, EK belongs to B. Okay? But I think this is a clearer definition. Okay, and what this lemma means is that if you have a measurable event, you can always approximate it with an arbitrary precision with an event that only depends on the state of finitely many edges. Okay, so actually this is not a new result. So for anybody that did measure theory, can you tell me what this result is? Okay. After I did measure theory, I immediately forgot about this result, so I think this is a normal reaction. But, okay, so, and again, if you've not done measure theory, just, well, listen to the noise and see if you like it, and just know that there are some things to learn if you want to fully grasp the depth of the theory. So, okay, so all of this comes back to the beginning when we define PP, okay? So PP is a product measure, okay? So it's defined on an infinite product space, a countable product space. And when you define the way to define the measures on countable product space is using Carat-Theodori extension theorem. Okay, so this is just the algebra of cylinder events. Okay, and what Carat-Theodori and you know that basically, okay, you can define the probability of events of this type, and you have to check that what you obtain is sigma finite, but this is what is done in the proof of Carat-Theodori theorem. So what this result is really the fact, which is an immediate consequence of the proof of Carat-Theodori theorem, that any element of the sigma algebra can be approximated by the element of the algebra. So okay, let me write it, proof. So. Okay, so the sigma algebra is sigma of A. Okay, so the lemma is just stating that any element of the sigma algebra generated by A can be approximated by a cylinder event. Okay, and I'm not going to redo the proof of this. I'm just indicating you where you can find this, the proof in a standard measure theory book. Okay. So this is kind of the first consequence of Carat-Theodori theorem. Okay, and if you look deeper at this approximation result, what the result says is that events with finite measure can be approximated. But here we have a measure which is a probability measure, so all events have finite measure. Okay, so I think this is really the most direct way of justificating this lemma. An alternative path would be to check that the set of events that can be approximated is a monotone class. But somehow, I mean, the monotone class theorem is more difficult than Carat-Theodori's extension theorem. So I think this is easier in a sense if you want to do it from scratch, from zero. Okay. Okay. So okay, so now come an exercise, which proves that the result that we have used several times until now, for all A measurable, we have PP of A is equal to PP T minus 1 V of A. Okay, so I'm not really answering the question because I'm giving this as an exercise, but basically the exercise is not too complicated now. this, okay, so first check that this is true for events in A. Okay, and for events in A, well, you have an explicit expression for the probability. Okay, it's just the sum over B bar of a product of P's and 1 minus P, and the expression is the same there and there. Okay, so first check this for cylinder events, then use this, okay, in a smart way, because you have to use this simultaneously for this and this, and then conclude. Okay, but basically proving this is kind of the same proof as when you want to prove that Lebesgue measure is translation invariant. Okay, you know that well, it's true for interval, and then kind of use of a result of this kind to extend it to all measurable sets. Okay. Okay, so now we are going to prove the theorem. So any questions so far? Okay. So, okay, so let me try to explain the basic idea. So maybe, okay, I will erase this. Okay, so how to explain this? So, okay, so let's say that I have an event which is translation invariant. Then, morally, without changing very much this event, I can make it depend just only on finitely many edges. So I can approximate very well this event by an event that depends only on finitely many edges. And all these edges, they have to be contained in the finite box. Okay, just take a box of diameter, the distance of the furthest edges to the center, to the origin. Okay. So now I have an event that depends on finitely many edges. And it's almost translation invariant because it approximates very well a translation invariant event. Okay, so because it's almost translation invariant, this event should not be very different from, okay, V times, okay, I take a very large number M, okay, such that if I translate M times by V, my two boxes are distinct, okay, and now I know that, okay, this event should almost coincide with this event because it's almost translation invariant. And on the other end, these two events are independent now because they depend on edges that are on disjoint sets. Okay? So what this means is that my original event, it's almost independent of itself. Okay, it's independent of itself up to a small error. But then I can make this error tends to 0, and I get that the event is independent of itself. And being independent of oneself is exactly having probability between 0 and 1, okay? If you show that you're independent of yourself, basically, you have PA equal PA square, and this means that P of A is equal to 0 or 1. Okay, so Okay, this makes me think of a second exercise of something that has not been questioned, but something that I've used, which is not completely trivial. So okay, so if A1 and A2 are events that depends on the state of disjoint sets of edges, then PP of A1, well, okay. Okay, so if events depends on disjoint set of edges, then they are independent. So somehow this thing is kind of easy if the set of edges, if A1 and A2 are cylinder events. Okay, because in that case, this is something that depends on finitely many edges, and okay. So, but okay, it turns out that when I did percolation on the tree, I used this also in the case where one of the events depending on infinitely many edges. Well, again, to prove this, basically, so this is harder than the first one. And to prove this, you're using the approximation theorem, okay, saying, I can approximate A1 and A2 by things that depends on finitely many edges. And, well, I can do it in a way such that these sets are still disjoint. Then I can pass to the limit. Okay, so this was a bit of a parenthesis. Here, in fact, I'm only going to use only going to use this for events that depend on finitely many edges. Okay, so I'm running out of space because now I have to. So. Let AN be a sequence of approximations of A. Okay. So the first thing I'm going to observe is that, well, the probability of AN tends to the probability of A, just thanks to this. So what we have is that, so what is it called? A. So A implies that A plus star implies that the limit when n goes to infinity of the probability of AN, it's equal to the probability of A. Okay, so now what should I do? Okay, so now I'm going to choose Mn such that only depends on the state of edges in minus mn to the d. Okay, so this I can always do. An, it depends on finitely many edges. If I take mn large enough, it will depend on the finite box. And now what I know is that An is going to be independent of a sufficiently translated version of it. So what I have is that pp of An tau minus 1 v mn An, well, it's equal to pp of An pp of tau minus 1 to disjoint boxes. Okay, so maybe I should put a 3 here to make sure that the edges are distinct, are disjoint. Okay, so remember V is a non-zero vector in ZD. So if I translate this box by V times Mn, then I get two disjoint boxes. Okay, because the L infinity distance here, it's larger than Mn. Okay, and now what I can say about this. Okay, now I'm using translation invariant of the probability to say that this is equal to pp An square. So this converge when n goes to infinity to pp of A square. Okay, so now what I have to do is what I'm going to prove now is that this also converges to pp of A, and then this will be fine because I know that pp of A is equal to pp of A square. Okay, so what can I say about? Okay, so now I'm just going to use. Okay, so just to make sure that I'm not. Okay, so just. Okay, here what I've used is that tau V composed Mn times is equal, okay. Composed N times is equal to tau Mv. Okay, so for this reason, if an event is invariant for tau V, it's invariant for tau Nv. Okay, so this is an important point, maybe. Okay, so the idea is if you're invariant for a small translation, then you're invariant for a large translation, and this allows to get you the independence you need. Okay, so now what can I say about the difference between this and this? Okay, and now I'm just going to drop the index in order to make the thing less heavy. So now I'm using A again to say that this is less than the probability of the symmetric difference of these two things. Then I'm going to use B, or is it B? Yes. So this is A. Now this is B of the exercise over there. So I'm just distributing this thing to obtain a union. And if I obtain a union, then I can bound by the probability of the sum. Okay, so now this thing is equal to 1 over n. So maybe I should just worry about this one. Okay, call it B star. Okay, but now I know that A is translation invariant. So for V and also thus for multiples of V. So what I get, this is the important part, is that A is equal to T minus 1 of A. Okay, now I'm using C to say that this is just T minus 1 of A n. And now I'm using the fact that my probability is translation invariant to say that this is simply PP of A. n. Okay, so this is also equal to 1 over n. This goes to 0. Okay, so if you have questions, please ask them, because in any references that I've given you, the level of detail of this proof is much smaller than this. Like everything is, I mean, basically is like the fact that the probability is invariant by translation and this kind of stuff. This is all considered obvious stuff, so that it's not discussed. So please, if you want to clear any doubt, now is the right time. Okay, so now we are basically done with the theorem. So, okay, maybe I can just shortly introduce what we are going to do next time. So now what we are going to study is basically a bit more the structure of the set of infinite percolation clusters. So the next important result that we are going to prove is the following. So okay, let me first do an observation. Okay, I mean, here so far I've written the proof in ZD, but if you want to make the same argument work on a tree, it's the same. Okay, if you have a periodic graph, basically ZD it's easier to write translation when you have a group structure on your graph. Okay, so this is kind of nice in order to have additions that are that is defined on our set of vertices. But this is not absolutely necessary, okay? You can define translations without that, and you could be fine. So, so what we are going to do next time is first to see a result which is still true for every kind of graph, and then prove for the first time something which is really specific to ZD. So, the theorem is kind of a refinement of the last theorem we proved. So let the infinity denote, okay, let's denote the number of infinite percolation cluster. For the realization omega. So the result is that Z is almost surely constant. Okay. And in fact, more than this, we have only 3 alternatives. So what we have is that either pp of z equals 0 is equal to 1. So this is when theta p is equal to 0. This is nothing new. Or pp of z equal 1 is equal to 1. Or pp z equal infinity is equal to 1. And this is, okay, when theta p is positive. Okay, so basically if you have a graph which is invariant by translation, you either have 0, 1, or infinitely many connected components. Okay, and so basically the proof of this is going to go into 3 steps. So the first thing is to prove this. And maybe I can tell you just now how it is, because it's almost, it's another consequence of the result we've just seen. So. Step 1. What we have is that for all k in, well, okay, in 1, yes, in n, okay, z plus if you want, union infinity, what you have is that the probability that z is equal to k. Okay, so what you have is that the event z equal k is translation invariant. Okay, so if I take all my edges and if I translate them, if I take all open edges and if I translate them by a constant vector, I'm not changing the number of infinite connected components. Okay, it's simply because I'm not changing the connectivity structure of the graph. Okay, because x connected to y in W is equal to x plus v connected to y plus v in TVW, omega. Okay, so it just means that the connective probability of ZD for for the percolated graph, it's the same as the probability of ZD plus V for the percolated graph with this environment. And well, the number of connected components is the same for it. Okay, so in particular, this means that the probability is equal to 0 or 1. Well, what I have is that well, the sum from k equal 0 to infinity of pp z equal k plus pp z equal infinity. This is equal to 1. So therefore, there is one term in the sum which is equal to 1. Okay, all the terms are either 0 or 1, okay, by the previous theorem. So there is one term that must be equal to 1. Okay, so this is the first step. The second step is to discard the possibility that you have finitely many but more than 2 infinite connected components. And well, now the idea is that basically, the idea of the proof, it's too technical to fit in now, and I think we've seen already there are already many stuff to digest. But the idea is that if you have k connected component with positive probability, then you will have one. Okay, if z is equal to k with positive probability, then you will also have z equal to 1 with positive probability. And therefore, well, this implies naturally that k must be equal to 1 if you don't want to have any contradiction. And the idea is simply that these k components, they have to intersect a given finite box. And then you only change probability by a constant factor if you open all the edges on this finite box. And if you open all the edges, then basically you're all connecting all these k components together, and you make them 1. So then on the modified configuration, you have one connected component, and this still has positive probability. So this is a bit hand-waving. You have to be careful if you want to make it this rigorous, but this is what we are going to do next time. Okay, and okay, and this is basically the second step. Then there is a third step which is a bit different, which is to say that this is actually what happens on ZD. Okay, so the number on ZD you only have one connected component. Okay, 1 or 0, but when theta p is positive, you have, with probability 1, you have one unique infinite connected component. Okay, but this is not, okay, this theorem is still not something empty. This thing can happen, and for instance, okay, I leave it for, I will restate it as an exercise for next time, but if you come back to the tree, you will see that on the tree, when P is larger than 1 over D, then almost surely you have infinitely many connected components. Okay, so on DD, this always happens. On the tree, this always happens. Any questions? Okay, so we'll resume tomorrow with this theorem and probably also with the theorem of the uniqueness in ZD. Okay.